So on to a somewhat different problem. It's still related to questions about minimal sets of connectives, but it comes at things in a slightly different way. So suppose you want to make a well-formed formula, and to use a fairly simple example, we'll stick to 3-sentence letters. And we want this formula to be true in certain specific rows and not in others. For this example, we'll say we want a formula that's true in row 1, row 4, and row 7, but isn't true anywhere else. Is there a way to do this that's sort of straightforward and easy and we'll always get the right answer? Well, there is, and I'd like you to think about it for a minute. Suppose that you're allowed to use not, and or. Set up a table with P, Q, and R, and put on the left all of the different combinations of truth values, and then try to think of a sentence built using not, and or that's true in exactly the rows 1, 4, and 7, and nowhere else. Pause the lecture for a moment, see what you come up with. Here's a solution. Here's our hypothetical sentence. We want it to be true in this row, and this row, and nowhere else. And here's what the solution looks like. I compressed things a bit here. I haven't put in all the brackets. These columns here just represent the overall result, but I think you get the idea. So here's how we're thinking about it. What's a sentence that's true just in row 1 and nowhere else? Well, P and Q and R. It's true exactly in row 1, not true anywhere else. What's a sentence that's true just in row 4 and not anywhere else? P and not Q and not R. It's going to be true exactly in row 4. And finally, a sentence is true exactly in row 7 and nowhere else. Not P and not Q and R will do the trick. What we want is a sentence that's true in exactly one of these 3 cases. If we put them together with an or, we've got the result. This or statement is true in either this row or this row. And if we say either that or this sentence that's true in the first row, then we get our result. So you see how this works. Associated with each row of the table is an and statement that would be true in exactly that row. We can get a sentence that's true in whatever specific set of cases we want just by taking the and statement that goes with each row and taking as many of those as we need and putting them together with or. That has a special name. It's called disjunctive normal form, and it's kind of a pretty way of representing in sentence form, if you like, what the table is telling us. It also has some useful and interesting connections to thinking about probability, but we won't talk about this now. However, what it shows is that absolutely any truth function whatever could be written using just not, and or. Absolutely any function whatever. And since we know that in principle we could get rid of the or alternatively we could get rid of the and, that tells us that absolutely any truth function whatever, even if it goes beyond the ones that our connectives might have made us think of, can be written using just not an and or not an or. But the disjunctive normal form has a kind of prettiness about it. So as we just said, any truth functional sentence can be written in disjunctive normal form, and any truth function can be expressed in disjunctive normal form. So as an exercise, try this. Write out the table for this, and then write a sentence in disjunctive normal form that says the same thing. I'm not going to give you the answer, but it's a useful little exercise to go through and do it. You should find that it's pretty straightforward. Now, one more topic, and it's this. Let's get the whole page visible here. We've talked so far about pairs of connectives that would be sufficient, but could we have a single connective that all by itself would be sufficient to express everything that we can express using all our connectives? And the answer is yes. The connective is just a downward stroke, and what it means is neither nor. So when we write P stroke Q, that means neither P nor Q. Now, okay, I'm going to ask you to pause again. What's the table for this connective? You should be able to come up with that pretty quickly. Using just this connective and the letter P, you might have to use it more than once. How can you write something that's true when P is false and false when P is true? In other words, something that says the same thing is not P. Using just this connective, how can you write something that means P and Q? Now, I'm going to let you think about that on your own, but once you've done it, here's what you've shown. You've shown that this one connective, it's called the Sheffer stroke after the logician Sheffer who introduced it, that this one connective all by itself could replace all our other connectives. So that's kind of a pretty theoretical result, if you like. It's also a result that has some practical use because a computer, in a way, is nothing more than a machine that solves very, very complicated truth table problems. It's got a bunch of binary gates. And so what we've said is that if you had just a gate or a switch that did in the computer what this does, in other words, that it was manipulating ones and zeros in a way that corresponded to neither nor, that one kind of switch or gate all by itself would be enough to do whatever any digital computer can do. You just need a whole lot of them strung together in the right way. So we've covered some territory here that, as I said, wouldn't be covered in the normal course of Philosophy 170. We've seen various ways that in principle we could strip down our system and we could come up with minimal sets of connectives all the way along to finding a single connective that in principle would allow us to say anything that can be said using truth functional logic.